Right, so this is a kind of lecture in two halves. I have to apologise, I'm an extraordinarily slow lecturer. I mean, every time I go back to the other lecture, I say, Colin says to me, how did it go? I said, fine. He says, oh, what have you done? And then, you know, his face goes like this when he finds out how little I've done. So, but I'm just going to finish off the last lecture, and then Colin's going to move on.
And then I'll be too fast. Someone else will have to slow me down. Right.
Okay, so if you remember, what we're doing is we're taking type judgments so these are things like and these are syntax, remember. There's syntax for types, syntax for terms, syntax for judgments that we've seen already. And we're converting them into not syntax, but into sets and functions. So this is, so we have, we're going to give a set that represents the context. A set that represents the type of the term. And it could be natural numbers, it could be function types, remember. And also, we're going to give a function that represents the term. So that's the program we started doing. And what we've done so far is, in the previous lecture, explain how to do this. Explain how to do this. And we started doing this. So I'm going to finish it off. So we did the rules for addition, we did the rules for variables, we did the rules for numbers. And they're all the simple rules. As ever, all the magic in the lambda calculus happens in abstraction and application. So here's our goal. So if we have the typing judgment, so that's a rule that allows us to say when a function type, when a term, which is a lambda abstraction, has a function type. In order to show that lambda x dot t has this type, you have to say, well, if x had the type sigma, then t will have type tau. So what I need to do, so given, the question is, what is that function? Well, one thing we know is the type of this term, this function has type okay, because there's the context, there's its type. So the interpretation of this term as a function takes elements of this set and gives elements of that set. And we know that this thing is the same as the functions from sigma to tau. Okay? So, how are we going to write this down? Well, we're going to use the information we have already. So we're going to say, well, I want to write down this function, but what do I know about the interpretation of this function? So I'm going to start a new piece of paper. So we know that, because we know this is true, we know that t is interpreted as a function from the interpretation of this context to the interpretation of tau. And we know that this thing is the same as the interpretation of gamma times the interpretation of sigma. So, So look, I've got this, and I want this. So now it's fairly straightforward. What I want to produce this, I've got enough information to make it, so I'm going to produce this. So what is it? Well, it must take something of type of in this set as input. So let's call it A, S, B.
Old-fashioned, I would call it lowercase gamma, but
okay.
just
all right.
Okay. You're off the bottom of the.
Ah, sorry.
Zoom out or scroll up.
Okay, so this function, it should take something in this set as input. So I'll give it something in that set as input. And then because this is the input in this set, this expression lives in this set. Okay, so I still have to give you this function. So I'll take something which lives in the input here, in this set, so S. And now I have to give you something in this set. I've never quite got the hang of that. Okay. So I have to give you something in this set, but T will produce that. If I give you something in this set and something in that set, I'll give you something in this set. Oh, I have something in this set. It's this. I have something in this set. It's this. Aren't I lucky? So it all fits together beautifully. So, almost done. So, that's this.
Yeah. I mean, you remember when we did like the call by value semantics, there was a whole thing about when you apply a function, you take the input and you put it in the environment. That's exactly what's happening here. So the behavior of the function, here's your environment, we get the next input, it goes into the environment, and then we explain what to do with the body of the function. So this, this is the same mechanism that you've already seen in the big step semantics. What we're getting here is that when we've got a typing judgment that says the program's well typed, that mechanism always works.
If you want to think about it this way, this is just an environment. You've seen lots of different environments. This is another environment, except these environments don't consist of terms or types. They're sets and elements of them. Okay, so we've done one of the two rules I set out to do. We've only got to do application left. So if you remember, the rule for application is, so finally, application. So the rule for application says, well, if I know that I have a term of type sigma arrow tau, if I know I have an input of type sigma, then I can make an application and I'll get something of type tau. So, again, I'm going to have some stuff and I want to make some stuff. So I have that f represents a function that A represents a function. So that's what we know, and what we want is the interpretation of f applied to A, which is a function which has this as input. So that's what I know, and that's what I want. So let's do it. So what is this? I have to define a function. It's going to take something in here as input, and then I need to make something of this set. So how can I do that? Well, f would eventually give me something in this set. So maybe I should use F. But then I need to give it something in this set as input. I mean, it's all clockwork. There's sort of nothing you can do. You have some inputs. It's like a jigsaw puzzle. Certain things only fit in certain ways. I have to give you something in the interpretation of gamma. Oh, I've got something in the interpretation of gamma. Aren't I lucky? So then this thing lives in this set, which is a set of functions from the interpretation of sigma to the interpretation of tau. So if only I had something in the interpretation of sigma, I'll get something in here. How can I make something in the interpretation of sigma? Oh, maybe I can use this. But this requires some input, but I have some input. And there I'm done.
Yeah. And again, this is not black magic. What we're saying is, to give the meaning of an application in an environment, you have to tell the environment to both the function and the argument. The function needs the environment, so does the argument. When we get back the meaning of the function and the meaning of the argument, we can finish the job and actually feed the input to the function.
Okay.
Right. So yeah, so we've got the sort of crucial payoff. Right? Always, when you have a type system, you're looking for a payoff. There are you're imposing some extra rules on programs, and the fact that you have obeyed those extra rules should buy you something, right? Otherwise, why are you spending energy complying with the regulations? It's got to be for something. And here we've seen that what it's for is that well-typed programs don't go wrong. We have seen that every single well-typed term in this lambda calculus really turns into a thing that works. So that's not the same as saying that everything that could possibly work is well-typed, but certainly the things that are well-typed definitely work. They don't go into a loop. They don't ever get stuck because you're trying to add a function to a number. We've done enough checking to make sure that the evaluation machinery is going to work perfectly and come to a finish, which is fabulous. So, that's a discipline of typing which results in a payoff. So what I want to think about for a moment, possibly for more than a moment, how long have I got? I've got half an hour. I want to think about doing the same thing for our other programming language. We've been thinking about lambda calculus a lot, but do you remember this old thing?
Oh, that's so big and verbose.
Yeah. What's going on with this language? So we've got integer expressions, and we've got commands, and we've got Boolean expressions, and there are like a bunch of things we could talk about here, right? We were very careful setting this language up to separate in the grammar the integer expressions from the Boolean expressions from the commands. And that as a practice, so that means that, that certain kinds of things that just don't make sense aren't even grammatical. But you think about how hard we had to work to do that. We're lucky we've only got integers and Booleans, right? If we wanted to do that for all sorts, if we wanted to throw in strings or arrays or any of that sort of stuff, all of a sudden, trying to make things make sense, just using the grammar to enforce compatibility would get pretty unsustainable pretty quickly. We need new grammatical classes for all the sorts of things. Also, the grammar here isn't enforcing that the variables that we use are even in scope. We can write down programs that use variables that we don't know the meaning of. They're grammatically correct, but the programs don't make sense. So there's some work that the grammar alone isn't going to do. We also paid a fairly high price in designing this language. You will notice that we have only got integer variables. And that means that variables only show up in the language of integer expressions. If we wanted to be more liberal and allow Boolean variables as well, then life would get a bit trickier. And what else is a source of misery? You can see that we've got like 2 new constructs. We had to have a new construct to allow you to introduce a new local variable in an integer expression, but also in a command. And that's because we've separated the integers from the commands. And back then, all we knew about was like grammars and dynamic semantics. So maybe we can get rid of some of this redundancy and enforce better safety properties and make things slightly simpler if we do less work in the grammar but add a static semantics. Let's figure out what would be a good type system for imp. Okay, so roughly speaking, here's my plan, expressed in 3 words. Smash the grammar. Just trying to get the zoom level right. So this document will appear on the web very shortly. So I've got one notion of expression. Oh, whoops, I missed some B's. That's bad. Where's the acetate? Sorry, my bad. That B shouldn't be there. There are now only expressions, and all hell breaks loose in expressions. Because I've got numbers, I've got bits, I've got these things called places, which at the moment are just variables. I've got curly braces with blocks. I've got operators, but I've only got one new. So everything has just been thrown together. We can write all kinds of crap. So here's an example of the kind of crap we can write. We can write if empty block 7 else the command that assigns true to x. That has become grammatically correct, even though it's utter nonsense. Isn't that great? The grammar is less complicated, it's got less duplication in it. Unfortunately, it's got much more utter nonsense that it allows. So we've got to figure out how to disallow the nonsense, not by putting the detail into the grammar, but by imposing a type discipline. You'll notice I have done one thing that's slightly sneaky. I've said that bits are now the keywords false and true rather than the digits 0 and 1. I do at least want to be able to tell bits apart from integers when I see them. So that's one stunt I've pulled in this construction. So you can see, yep.
What's the operator that's like a backslash and a
Oh, right. Oh, this is actually a formal grammar, and because vertical bar is used to separate the options, if one of the operators is actually a vertical bar, it needs a backslash to escape it. So that's just or. Yeah. But in order to name it in the context of a grammar, I have to escape the name. Yeah, this is literally compiler syntax for the grammar. Okay, so we're going to need some types. Let's think what types we're going to need. Well, we have integer expressions, integer stuff going on, so we're going to need a type of integers. We have Boolean values going on, so we're going to need a type of Booleans. But we also have commands. So, and commands are jumbled up in the expressions as well. So in order to say, actually, this thing is just a thing we do rather than a thing that gives us an interesting answer, we'll need another type for those things. And in imperative languages that you're used to, it's traditional to call that type void. So we're going to have a whole three types, right? Not infinitely many types, like in simply typed lambda calculus. A whole three types: bool, int, and void. And where void is just the type of commands. And what are we going to need to be able to figure out whether programs make sense? Well, no. That's a piece of technology. What's the idea that we're going to need in order to figure out how to make a compiler that tells if a program makes sense? Right. You've got some programs that do a bunch of stuff. What do we need to, but the programs have got variables in. You kind of hope that if we know the types of the variables, so previously we've only had integer variables, but I'm going to say let's allow Boolean variables as well. If we know the types of variables, we ought to be able to say whether a program is okay. Right. So let's see if we can build the setup. Right. So, in lambda calculus, how did we explain the types of the variables? The thing that did that job was the context. So we're going to need to have the same sort of thing. So we've got our types are void or integer or bool. Our context.
Page down, Connor.
Yeah. Well, that's the thing. I don't have eyes in the back of my head.
For 8 weeks, I've been doing it wrong.
Yeah, and you lot, because you would rather not see what's going on, because it's like peril-sensitive sunglasses, right? Never say a word, because you won't even lift a finger when it's blatantly in your own interests, because you know you can always blame us when you screw up.
Oh, I got a reaction.
Right. So, context is just going to tell us which variables exist at all, which variables are in scope, and what their types are. And then we're going to have a judgment form whose job is to say what type of thing you can put into a variable. And I'm going to write that judgment like this. Today I'm going to write it like that. So this judgment means, according to context gamma, x is a variable that you can shove values of type tau into. Yeah? So it just says, gamma lets us put taus into x. All right? There are two rules. If the context finishes, so we always keep the local end of the context on the right. If the context finishes by saying x has type tau, then guess what? It's okay to put values of type tau into x. So we got lucky. The variable we were looking for was on the top. What if the variable we're looking for isn't on the top? That's to say, what if we were in a situation where we have y of type sigma on the top, but we are looking for x, and x is not y. Well, then we carry on looking. If gamma says you can put taus into x, and you stick something else on the top of the context that isn't called x, that doesn't shadow it, then it's still okay to put taus into x. Everybody fine with that? So we've just explained the scoping rules for imp, right? Remember, in imp, you can have lots of variables with the same name, because new allows you to introduce new variables with the same name as old variables, and the rule is that the most local one wins. And we have just written down more formally, the most local one wins. That's to say, you can always take the top one, and you can look below the top one if the top one has the wrong name. So we're going to find the rightmost thing called x. Okay, cool. We know about types of variables. It's time to figure out how to give types to expressions. All right, so we can do a bunch of boring rules, you know. If somebody gives us a number n, that's going to have type int. If somebody gives us false, that's going to have type bool. And, you know, true is also going to have type bool. Moving on up, actually zooming out a little. What about?
I've never worked that out.
Yeah. What about variables? If we see an expression which consists of a variable, how are we going to figure out what type it is? Well, we're going to look it up in the context. So if the context says the variable is of type tau, then as an expression, the variable has type tau. That says whatever sort of thing you're allowed to store in a variable, that's what you get when you make use of the variable. Shocking. So we've got rid of the fact that variables are only integers. We can make them whatever we like. But then we have to think about assignment, because this is now an expression. This is an expression, so it ought to have a type. When does it make sense? Well, are we allowed to assign to variables if they are not in scope? No. So we had better check that they are in scope, and also it might be a good idea to find out what type of thing you're allowed to store in the variable. So we look x up in the context and we discover that it stores values of type tau. Now, here's a difficult question. What should we check about E?
If it's also type tau.
Exactly. We're hoping that evaluating E will give us a value that we're allowed to store in the variable. So E better have type tau. Now, what is the type of the whole assignment? It might be tempting to say that it's tau, but remember, an assignment is something that we do. It's not something that gives us our value. So the whole assignment has type void. That's to say, we have to check that, that the expression has the right type to generate values that can go in the variable, but we execute the assignment for the effect of putting that value in the variable, not to get our hands directly on the value. All right, bunch of other stuff we need to do. Oh, there was another stunt I pulled with the syntax. Let's look at the expressions. Is there anything else you can spot that has mysteriously vanished? I've got rid of one construct. Do. I've got rid of do. So remember, this was do. It allows us to do a command and then follow that by evaluating an expression. I have a sneaky plan involving blocks and semicolons. What's going to happen is that when we execute a block, right, a block is 0 or more expressions in a sequence. The idea is that we'll just get whatever the last thing is in the block, we'll compute that. So if the block finishes with an integer expression, we'll get an integer. If a block finishes with a Boolean expression, we'll get a Boolean. If a block finishes with a command, we'll just get void. And if a block is empty, we'll just get void. So the idea is the type of a block is going to be void if it's empty, or the type of the last thing in the block if it's not empty. So more rules for expressions in a moment, but I'm going to do blocks. Better zoom out again. Here's my typing judgment for blocks. Just trying to be consistent. Right. So the idea, better move up a little. The idea is that we've got two types kicking around. Sigma is the type of the last thing we saw before we execute, before we have these E's to execute. It's the type of the last thing we saw. And tau is the type of the last thing we end up with. So imagine we're, well, I'll show you how it goes in these rules. If the block is empty, empty block, and sigma is the type of the last thing we saw before it started, then sigma is what we give back. And otherwise, we've got a non-empty block. And we have to say what type it has. So what we do is we figure out the type of E. And then we install that, so that's some sigma prime. We install sigma prime as it's now the last thing we've seen before we start E's, and out comes tau. And since tau comes out from the end of E's, tau comes out from the whole thing. So all I've done, this judgment has a little extra, like a memory of the type of the last thing we saw. And every time we type check an expression in a block, we remember its type in case it's the last thing in the block. So that when we eventually reach the end of the block, the thing we remembered as the last type we saw is the type we give back for the whole block. See what's going on there? And then the rule for blocks is that if we kick off with void, and out comes tau at the end, then out comes tau. So remember, that's delivering the logic I promised you. If the block is empty, its type is void. If the block is not empty, its type is the type of the last thing in the block. So now we can get rid of do return, and we can just write a block that contains a command followed by an integer expression, and that will give us, because the type of the second thing is integer, the whole thing will be an integer. So we've saved some ink there. I think, I'll do one more rule and then stop.
Actually, Connor,
Yeah?
they've asked for
Yeah?
things to think about. So often I leave them with, think about this.
Yeah.
Maybe
I'm factoring in that.
Okay.
I'm going to do if, and then ask you to think about while. Okay, we're checking an if-else. What do we need to be sure of? What about the condition? How do we check the condition? What would we like the condition to be? Would we like the condition to be 7?
This would be a Boolean.
We would like it to be a Boolean. What about the then branch? I mean, in the past, we insisted that it was a command. But do we really care that it's a command? I mean, wouldn't we maybe like to use if-else to choose between two numbers instead of between two commands? Why not? Why should if-else only be about commands? Let's be as liberal as we can. Let's just say it can be any old thing. But now what about the else branch in the case where the condition is false? What about that? We said that the then branch has type tau. What type should the else branch have?
Tau as well.
Tau as well, because depending on the condition we're going to get one or the other, and they're going to have to plug into the same places. So indeed, the type of the whole if is like that. So here, we can use the fact that we are allowed to have, even though only 3 concrete types exist, the fact that in the typing rules, we can have meta-variable tau standing for any old type we like. We've just said, you can now use if to choose between integers, or between booleans, or between commands, same construct, one rule. Now, to finish off with a thing to think about, what should be the rule for while? Let's talk about that next time. What conditions do you want to impose on while?
What a cliffhanger.